J'espère que vous allez tous sur YouTube à la fin des séminaires. On a Santiago qui est chez nous en thèse et qui va nous présenter des résultats sur Analytical Conformal Bootstrap for non-diagonal 2D CFTs.
Thank you. Well, thank you all for being here. Good morning. And thanks, Vincent, for the introduction. So I will talk about some recent work that we did with my advisor, Sylvain Ribaud, and that you can find on archive under this number. So let me begin with a short introduction about conformal symmetry. Conformal transformations are transformations that preserves angles. In particular, we have rotations, translations, changes of scales, and some more complicated maps, for instance, the one that sends the sphere into a plane. And in particular, in 2 dimensions, any transformation of the form C going to f of C with f holomorphic function will define a local conformal transformation. The symmetry algebra that encodes these transformations is the infinite dimensional Virasoro algebra, which is characterized by a parameter called the central charge, C. And the value of C will determine many of the properties of the theory we're studying, and in particular, if we look at CFTs that describe critical points of statistical physics system, different values of C will determine which model we are describing. And so for C equals 0, we have critical percolation, C equals 1/2 is the Ising model, and C equals 4/5 the 3 states post model, and so on. In this case, we will consider a theory where we have a full algebra made of 2 copies of the Virasoro algebra with the same central charge, and which we call left moving and right moving. So what does it mean for a field theory to have conformal symmetry? Well, first of all, it means that our fields will fall into representations of the symmetry algebra B times B. And so if we have a representation of the product algebra of the form R delta times R bar delta bar, will denote a field belonging to such representation by the 2 conformal weights delta and delta bar. That the fields belongs to a representation of the algebra means that when we perform a transformation, it will transform in a certain specified way. So if we perform a dilation sending C to lambda times C, we find that the field transforms with the power of lambda given by the sum of both the conformal weights, called the conformal dimensions. And if we perform, for example, a rotation, we find the phase factor given by e to the minus I times the difference between the 2 conformal weights and the angle of rotation, and the difference between the 2 weights is called the spin of the field. So the spectrum of the theory will be the set of all the representations corresponding to the fields of the theory, and in particular we can distinguish from the spectrum 2 types of theories. First of all, we have what we call diagonal theories, which are those in which the representations appearing in both the left moving and right moving sector are always the same, and thus this produces only fields with 0 spin, because both conformal weights will be the same. And on the other hand, we have non-diagonal theories in which we allow these 2 representations to be different, and thus we can have, in this case, representations with non-zero spin, fields with non-zero spin. In this talk, I'll be interested in non-diagonal theories. For example, they are thought to describe certain limits of critical percolation of the Potts model. And we can have a look at the sort of a map of some of the known solvable models in CFT. So for central charge larger than 1, we have Liouville theory in all this line, and then we have its analytic continuation to the rest of the complex plane of the values of the central charge, except for C less or equal to 1, where we have to change a bit the solution, but we again have a CFT which we call Liouville, but with c less or equal to 1. On the other hand, for these discrete values of the central charge given by two prime integers p and q, we have the so-called minimal models, of which some can be unitary, represented by these lines here. The minimal models are dense on the line c less than 13. And in particular, we can distinguish two types. We have the A-series minimal models, which are diagonal models. So we have only fields with zero spin. And we have D-series minimal models, which contain a non-diagonal sector in their spectra. There are other types of models, but these are the only ones I'll mention here. And then we have, for instance, for C equal 1, we have the critical point of the Ashkin-Teller model, which is again a non-diagonal theory, and the critical point of percolation, which again is thought to be non-diagonal. So our aim in this talk is to see if, by means of the conformal bootstrap method, we can pinpoint another points in this map corresponding to solvable and consistent non-diagonal CFTs. So we will use the conformal bootstrap approach in order to explore the space of theories that we can find. So when studying field theory, what we want to find are, on the one hand, the spectrum of the theory, and on the other one, the correlation functions between fields. But in the case of conformal field theory, 2- and 3-point functions are, well, their space-time dependence is entirely fixed by symmetry. The 2-point functions between two fields B1 and B2 will take this form. It will only be non-zero if both fields are the same. And then it goes as a power of the difference between the 2 points in which the two fields are inserted. And we have also here a factor which we call B of depending on the dimensions of the field, which is in principle can be fixed by normalization, but for the moment we'll refrain from any such choices. On the other hand, the 3-point structure constant again has a space-time dependence that goes as a certain power of the difference between the different points, where the exponents are combinations of the conformal dimensions. And then we find a constant called the 3-point structure constant, which does not depend on C. It's only given by the dimensions of the fields, and which, contrary to this coefficient here, it cannot be entirely fixed by normalization. So when trying to solve the CFT, one of our goals will be to find what is the expression of these constants. Now, in the case of 4-point functions, now the dependence on the space-time coordinate is non-trivial because we have a conformally invariant cross ratio on which they depend. And we are interested in computing the 4-point functions not only because they are the first non-trivial one, but also because in performing this computation we'll find constraints on the 3-point structure constants, which will allow us to solve the theory. So in order to compute this 4-point function, we'll resort to the operator product expansion of the theory, which means that whenever we have two fields inserted next to each other, then we can expand that product inside a correlation function as a sum over some spectrum S of fields belonging to that set times some coefficients given by the 3-point structure constants and the normalization factor of the 2-point function. So if we insert this expansion into the 4-point function, we find what we call in this case the S-channel decomposition of the 4-point function. Again, we have a sum over a certain spectrum corresponding to the channel S of some coefficients that now have two 3-point structure constants and the normalization factor of the 2-point function, and this coefficient as a whole is called the 4-point structure constant D. And then we have a series of known functions which are determined from the algebra that are called the conformal blocks. So if we want to compute the 4-point function using this method, since the conformal blocks are in principle known, what we need to find out is the spectrum over which we are performing the expansion and the 3-point structure constant. So how should we go about finding this? One method is to try to profit from the so-called crossing symmetry condition, which means that while here we have used the OPE between the fields 1 and 2, we could have used equally the OPE between the fields 1 and 4, and thus we would have obtained a different expansion for the same function. This gives the so-called crossing symmetry constraints, which are at the heart of the conformal bootstrap approach. And there are an infinite set of equations that, if they could be solved all at the same time, we would find conditions constraining the spectrum on both channels, so the S and T channel spectrums, and also the 3-point structure constants. So if we were able to solve the system generically, we would find all the information that we need to compute all the correlation functions that we want, and thus would have solved the theory. The problem is that the system is too hard to tackle generically, and thus we need to resort to some simpler form of these constraints. And for this we will use the so-called degenerate fields. Degenerate fields here are denoted by the indices 2, 1 and 1, 2. And they have the special property that in the expansion of the 4-point function that involves these fields, we find only finitely many terms. This gives rise to a simpler system of constraints, which we will be able to solve and find the 3-point structure constants and the spectrum. So let me give you an overview of what I'm going to do next. First, I will see which constraints on the form of the non-diagonal spectrum we can find or are imposed by the assumption that we can indeed take the OPEs with the degenerate fields. Then I will move on to writing explicitly the degenerate crossing symmetry constraints and finding equations for the structure constants. And from this point on, we will take two paths. First of all, I will discuss the explicit solution for the 3-point structure constants in a non-diagonal theory and the relation to a diagonal theory. And then I will move on to the computation of crossing symmetric 4-point structure constants. But for this, we will need to have an answer for the non-diagonal spectrum, which we will find by studying a certain limit of the known non-diagonal minimal model. Yes?
Could you please say why one of the legs is dashed?
Oh yes, this is a diagrammatic expression to say that this is a degenerate field.
Okay.
But it's non-standard, okay, just to have it here. But think of it as just seeing the crossing symmetry constraints involving these fields. So, well, and I should have said the method of studying the degenerate crossing symmetry constraints is called the analytic conformal bootstrap, and it is what I'm about to do now. So, first point, constraints on the non-diagonal spectrum. So, our assumptions in solving or in studying non-diagonal CFT will be, first of all, that we will impose all correlation functions to be single-valued. This means that if we take an endpoint function of fields of the theory and perform a rotation, we find a factor depending on the sum of the spins of all the fields. And if this rotation is by 2 pi and we ask the endpoint function to be single-valued, then what we find is the constraint that the sum of all the spins in the endpoint functions should be an integer. If in particular we study this in the case of the 2-point functions, we find that the spins of all the fields should be half integer at most, and we will take this to be a constraint on all the fields that we will allow in our non-diagonal theory. So the next important point is that we want to be able to compute operator product expansions involving degenerate fields. These OPEs are better expressed in terms of new parameters. So let me introduce the parameter beta for the central charge, and now we'll express C as 1 minus 6 beta minus 1 over beta squared. And in terms of this, and also the parameter p, the momentum for the conformal dimension, in which as a function of which delta is expressed in this way and analogously for delta bar, and the spin written in terms of the momenta is just the difference between the squares of the left moving and right moving. Now, in terms of this notation, we can express the known fusion rules involving degenerate fields, and we see that in principle each OPE could have so these fusion rules allow each OPE to have at most 4 terms, because we are performing a double sum here between on the parameters epsilon and on the indices epsilon and epsilon bar. This is a spin.
The first part was right.
It's the difference between the left and right dimensions. But in terms of P, because this term is the same. So again, if we look at the known fusion rules for the degenerate fields, we find that in principle each operator product expansion would have 4 terms. We see that the field 1, 2 will shift the momenta of the other field by beta over 2, plus or minus, and the field V1, 2 will shift the momenta by 1 over 2 beta, again plus or minus. So we need to see of these 4 terms which ones we can retain, and so let me take the OPE with the first degenerate fields. We have the 4 terms here, but we need to ask that each of these satisfy the half integer spin constraint. If we compute the spins of the fields on this side, we find that this constraint will only be satisfied provided we have P minus sigma P bar belonging to this set, 1 over 2 beta times an integer, where the parameter sigma is now the product of the 2 parameters involved in this sum. So when looking at this OPE, we have 2 terms in which the momenta are shifted in the same way, so we have epsilon equal epsilon bar and sigma equal 1. And conversely, we have 2 other terms in which the momenta are shifted differently, and thus for those 2 sigma equal minus 1. So if we think that if we want to retain the 4 terms in the OPE, we need that this condition is valid for both values of the parameter sigma. And this in turn would mean that the spin of the original field B here that takes its form should belong to this set, 1 over 4 beta squared times the integers. But the problem is that if we also want the spin of this first field to be a half integer, we would be imposing a constraint on the value of beta squared. In particular, we would be asking of it to be rational. And in particular, in this talk, we will try to keep the central charge generic. And so in order to do that, we cannot impose this constraint. So we will say that this condition here only holds for 1 value of sigma, and thus only 2 terms will be present in the OPE here. We can perform the same reasoning starting with the other degenerate field, and thus we'll find a very similar condition with now a parameter sigma tilde and a change of beta going to 1 over beta. And so for each field to have well-defined operator product expansion with the degenerate fields, we need these conditions to hold both at the same time, each for only 1 value of sigma and sigma tilde. Said in other words, we will consider that each field carries also the indices sigma and sigma tilde, which determine their OPEs with the degenerate fields in the following way. So we see here that sigma will determine how the momenta are shifted relative to one another in the OPE with the first degenerate field, and sigma tilde will do the analogous in the other OPE. And notice also that the value of sigma on the left of sigma and sigma tilde on the left hand side and on the right hand side are always the same, because the momenta on this side and on this side will satisfy the same conditions. So if for each field we need to give the values of sigma and sigma tilde, let's see what kind of solutions we can find. we find that depending on whether sigma and sigma tilde are equal or different, we have two types of field. We call diagonal fields those which have sigma equal sigma tilde, and we can, without loss of generality, set them both equal to 1. In this case, we find by solving these two equations that the left and right momenta will be equal to one another, so we only need to identify the field by one of them. And of course, this will produce fields which only have zero spin. On the other hand, if we have sigma different from sigma tilde, then inserting this into these equations, we find that the momenta should have a specific form given by two numbers r and s. What we find is that the left moving momentum should be of the form PRS, which is 1/2 r times beta minus s over beta, and the right moving momentum should be of the same form but with this sign over here flipped. These fields will have a conformal dimension given by this expression over here below, and their spin is given by the product of the two numbers r and s. In particular, the half integer spin condition will force this product to be itself a half integer, and also each of the numbers r and s should be itself a half integer because of this 1/2 factor we find here. But notice that it is not enough to know the momenta of a field to identify it as diagonal and non-diagonal, because we could have, for instance, a non-diagonal field in which the s index is 0, and thus its left and right moving momentums will be the same. So let me show you in this case what really will distinguish the diagonal field of momenta p r0 and the non-diagonal field of indices r and 0 is the fusion product with the degenerate fields. In the case of the diagonal field, if we take the OPE with the degenerate field 1, 2, we find that the fields appearing in the OPE will continue to be diagonal. Now the momentum will be of the type p r epsilon, but both the left and the right momenta will be equal, and the epsilon will only appear in here. And of course, since the fields appearing here are diagonal, we find that on the right hand side we have all fields with 0 spin. On the other hand, if we perform the same OPE but on the non-diagonal field, we find again that here we have the index epsilon, but now the left and right momenta are different. They differ in this sign here, and the fields on the right hand side have a spin minus epsilon times r. So even though we started with two fields with the same momenta and 0 spin, both of them, when taking the OP with a degenerate field, we find that in one case we produce spinless field, and in the other they are spinful. So the moral of this story is that it's not enough to know the momenta to characterize a field. We also need to know how they fuse with the degenerate fields. Okay, so we have found that asking to have consistent OPs with the degenerate fields imposes constraints on the spectrum. Now let me use the OPs, these degenerate OPs, to write the crossing symmetry constraints. If we write the OPE with the degenerate field in this way, this abbreviated way, we find the S and the T channel decompositions, where now F and F bar are represent each of the conformal blocks. And we find a constant here that's a degenerate 4-point structure constant, which contains the product of the degenerate OPE coefficient and a generic 3-point structure constant. So yes, so this is why by studying these degenerate 4-point functions, we can actually find constraints on the generic 3-point structure constants. Now the S and T channel conformal blocks represent only two bases of for expanding this function, but we can relate these bases between each other, and thus we can compute exactly the ratio, for instance, of the two S channel coefficients. This ratio will give it the name rho here, rho of B1, B2 and B3, where the first field is the one with which we are taking the OPE, and it takes the following explicit form as a combination of gamma functions depending on the momenta. I will only point out that we can clearly separate it into a factor depending only on the momenta of the first field, and then another factor which depends on all three momenta together. So since the degenerate 4-point structure constant here can be written in terms of the 3-point structure constant, we can write an equation determining the ratio of two 3-point structure constants in which the momenta of this field and this are slightly shifted. And if we manage to solve this equation, then we will find constraints, we will find the form of the 3-point structure constants. But all of this, of course, holds provided that there exists a non-trivial solution for this 4-point function, that is, provided we can write this expansion with coefficients here that are non-zero. And this will happen only if the sum of the S indices of the non-diagonal fields is an integer. So take into account here that the index is defined in terms of the difference of the momenta. So this means that diagonal fields will have always indices 0 because they have the same right and left momentums. And if we perform the same reasoning again with the other degenerate field, we find an analogous constraint. Now we can understand this constraint as a property of the 3-point structure constant, and thus we say that these constants will be non-zero only provided that the sums of both the indices R and S are both integers. This has consequence on which kind of 3-point functions we can have. For instance, if we were to compute a 3-point function between two diagonal fields and one non-diagonal field, this would only be non-zero provided both the indices of the diagonal fields are both of them integers. Otherwise, this function will always vanish. But provided these non-triviality conditions are obeyed, we have the equation for the 3-point structure constant, which for the moment involves the degenerate OPE coefficients. This could in principle be set by normalization, but again we are trying not to impose anything yet. And we have an analogous equation that comes from the other degenerate field. Now if we want to write an equation for the 4-point structure constant, we can do so starting from this one because it can be written in terms of the 3-point structure constants. But we have again this factor that could be annoying. So if we study a simpler 4-point function which involves twice a degenerate field and only one other field, generic, we find a simplified ratio involving the degenerate OPE coefficients and the normalization factor of the 2-point structure constants. This ratio takes this explicit form here, and thus combining this simplified ratio with the ratio rho we defined before, we can write equations for the 4-point structure constants that do not involve neither the 2-point normalization factor nor the degenerate OPE coefficients. And since we know this ratio here explicitly, we can use it to compute the 4-point structure constants, for example, iteratively with a computer. We could also find an explicit solution, but the equations are enough to determine the structural constants. So now we've seen how the degenerate OPE crossing symmetry constraints impose equation 3-point structure constants. In total we have 4 because we have 2 more with the other degenerate field. Now let me discuss the solutions, in particular in the case of the 3-point structure constants. So in order to discuss the solution, I first need to tell you what we can determine through this method. And what I mean is that the crossing symmetry constraints will not fix any normalizations because we are comparing two expansions, but any normalization term in those in each of those expansions will cancel on both sides, and thus we are unable to determine them. So if we split the 3-point structure constants into a normalization dependent part, which we call the factor y of b, and a normalization independent part called c prime, we see that under a field redefinition b going to lambda of b times the original field, the factor y transforms linearly with lambda, and the 2-point normalization factor transforms quadratically. And so we can determine that we reach the conclusion that the normalization independent quantities that we can find are c prime for the 3-point structure constants and this combination of the factors y and b. But again, this is enough to compute 4-point structure constants because the 4-point coefficients can be expressed in terms of c prime and the normalization independent factor, and then this product of normalization dependent quantities will cancel on both sides of the crossing symmetry constraint. So the question now is, how do we determine the normalization independent part of the 3-point structure constant c prime? If we define in a similar way as before the ratio of the normalization independent parts as being rho prime, we see that the ratio between the original ratio rho and rho prime should give a factor that depends only on the dimensions of the first field. And thus if we find an ansatz for c prime such that rho prime can account for the dependence of rho on the 3 fields, then we would have find a suitable solution for the 3-point structure constant. And then once we have once we have rho prime, we can write the equation for the other normalization independent quantity in terms of rho prime, and the simplified ratio I showed before. So we have indeed found such an ansatz. It takes, in the case where the first of the fields is taken to be diagonal, the solution is a product of double gamma functions which are defined by this shift property of its arguments, along with the fact that it's invariant under the change beta going to 1 over beta. And we can see that, well, by using these properties, we can check that it actually accounts for the dependence of the ratio rho on the 3 momenta. And then we have here above, we have a sign factor f, which is always plus or minus 1, and which is determined by the following, again, shift properties of its arguments in terms of the indices of the other fields appearing in the structure constant. So, for example, if we have a diagonal theory, these indices would be 0 and f would always be 1. If we have a theory with non-diagonal fields but which have always integer indices, again f would always be 1. But in a more general case, we would need to determine f, for instance, by recursion for each structure constant. Now, using this solution for the normalization independent piece, we find the solution for the other normalization independent quantity for a generic field which could be diagonal or not, which includes again a product of double gamma functions and a sign factor which is minus 1 power the spin. So now that we have a solution, we can ask what is the relation of this solution with those known for the diagonal case. So the first thing we do, now restricting ourselves to c less or equal to 1, is we evaluate our ansatz in 3 diagonal fields, and we find that it can be expressed as a product of upsilon functions, which are a combination of double gamma functions, which happens to be the 3-point structure constants for Liouville theory with c less or equal to 1. So we see that we reproduce the structure constants of the known diagonal theory for the same values of c, but furthermore, if we take the square of these 3-point structure constants in the generic case, we find that we can express it as a product of 2 Liouville structure constants evaluated on the left and on the right momenta. This can also be expressed as a geometric mean, if you want, saying that the structural constants of the non-diagonal theory is the geometric mean of two constants of the diagonal theory. This expression appeared, for example, in a paper by Benoit Estienne and Yassine Clef in 3 years ago now, in which they studied the Owen loop models and the non-diagonal CFT that would describe them. They found this expression. And though if we wanted to start from here, it would probably not be as useful because we need to determine the sign with which we take the square root. And also, even though these structural constants here could be analytic, we need to check that taking the square root does not spoil this analyticity. But by finding an explicit solution for generic non-diagonal theories, we found that this can actually be done. And nonetheless, this expression can sometimes be useful. For example, if we were to compute the four-point function with only two different fields, 1 and 2, then the four-point structure constant would involve squares of this constant here, and thus we can directly express it as a product of the Liouville three-point structure constants times the normalization independent factor that we had determined before. So now that we have gone over the explicit solution for the three-point structure constants, let me go back to attempting to compute four-point correlation functions. We said that four-point functions can be expanded in this way, where we have the conformal block and now the four-point structure constant, which is determined by these equations here, where rho tilde is just the analogous to rho corresponding to the other degenerate field. But we still have a missing piece. We still have not determined what the spectrum over which we are summing should be. And for this, the degenerate crossing symmetry constraints cannot provide an answer, because in that case the spectrum of each OPE is already fixed. So we need to look somewhere else to find inspiration for determining this spectrum. And thus we turn to studying a limit of non-diagonal minimal models, which are in this case the D-series minimal models. These are rational non-diagonal CFTs that exist for rational values of the central charge given by two coprime integers p and q, where we are taking q to be equal to 2 modulo 4 and p to be odd. Then the spectrum of these theories contains a diagonal sector in which we find only fields with zero spin, because we have the same representation left and right, and a non-diagonal sector in which we find now fields that have a spin. And we'll be interested in taking a limit of this part to see if we can produce a spectrum for our four-point functions. Furthermore, these theories have an interesting feature which we call conservation of diagonality. That means that if we take the OPE of two fields, one diagonal and one non-diagonal, then we will get a sum over the non-diagonal sector of the spectrum, this one. But if we take the OPE between two fields that are of the same time, we'd get an expansion over the diagonal sector of the spectrum. So taking this into account, if we manage to take a limit of this theory and produce a non-diagonal spectrum for the limit, then this would correspond, in our non-diagonal theory, to the spectrum of the expansion between diagonal and non-diagonal fields, because we want this property to hold even after we've taken the limit. So what is the limit I want to take? I want to send p and q to infinity such that c approaches some non-rational value c0. Here this should be less than 13, sorry, that's a mistake. But since the values of the central charges in the minimal models are dense on the real line, c less than 13, we can in principle take this limit. Now let's have a look at the non-diagonal sector of the spectrum. all the representations that appear here have integer spins that are given by this expression r minus q over 2 times s minus p over 2, where q over 2 is an odd number. Yes, q over 2 is an odd number. And so what we want is to take this limit, but we will do so by keeping these spins constant. So we defined r to be q over 2 plus a number r0, which will be even, and s to be p over 2 plus s0, where s0 is a purely half integer number. So when taking p and q to infinity, r and s will go to infinity in this way, but the spins and furthermore the dimensions of the representations will remain the same, and we can express the limit. We call this limit the spectrum S to Z plus 1/2, which is composed of infinitely many non-diagonal representations where the momenta take the form PRS and PR minus S for the right moving part, where R, the first index, is always even, and S, the second index, is always half integer. So in this spectrum also the spins will always be integer because they are given by the product of both indices, and we point out that the lowest dimension of this spectrum corresponds to the field of indices 0 and 1/2. This spectrum appeared in a paper by Sylvain Ribaud and Raoul Santaquiera in 2016, in which they related certain correlation functions involving these fields and this spectrum to a critical limit of to a critical point of percolation in 2 dimensions. So that is also it's nice to see it appear also in this way. So our ansatz for the spectrum will be this one, and as we said before, it will appear whenever we take the OP between a diagonal and non-diagonal field. And finally, let us point out that the conservation of diagonality of the minimal model is enforced also by the conditions that we find in the conformal bootstrap approach, because if these non-triviality conditions impose that the sum of the S indices should be an integer in order for the function, for a correlation function, to be non-zero, and thus in this case, if we take a 3-point function with 2 diagonal fields and 1 non-diagonal field, we find that it will always be 0 because the index S3 of the third field is a half integer. So this condition is not satisfied. So even though we said that we wanted this property to hold as a part of taking the limit, it's also interesting to see that it was already enforced for this spectrum because of the degenerate crossing symmetry constraints. So now that we have an ansatz for the non-diagonal spectrum, we can finally compute 4-point correlation functions. We will take a 4-point function which contains 2 diagonal fields and 2 non-diagonal fields belonging to this spectrum. Then the S and T channel expansion will both be over the spectrum 2Z, Z plus 1/2. The 4-point structure constants will be determined by the equations I showed you before, and the conformal blocks of each channel are known. So we conjecture that this function should be crossing symmetric for any central charge in which the real part is less or equal than 13, when the non-diagonal fields belong to the spectrum I described in the previous section, and we leave the momenta of the diagonal fields to be arbitrary, and in particular they could be continuous. So let me mention that the code that we use to perform these computations of 4-point function is available for all of you to play with in this address. And now I show you the first example. This is a 4-point function which has only two different fields. The value of the central charge has been set arbitrarily in the same way as the value of the dimension of the diagonal field. The non-diagonal field that appears here has a spin 3, and we find that the agreement between the two channels S and T is is rather good. It's almost always of order 10 to the minus 10. So from looking at this example, we conclude that this function satisfies crossing symmetry, or it does enough for our criteria. But now let us and yes, it's maybe interesting to point out that the 4-point functions that were related to the limit of critical percolation were of this type, were exactly of this type, where all the fields had the lowest conformal dimension in the spectrum. But let us move on to a more generic example. Here we have finally 4 different fields, 2 diagonal and 2 non-diagonal. Again, both the central charge and the dimensions of the diagonal fields were set arbitrarily by hand. And then we have a non-diagonal field of spin 0 and a non-diagonal field of spin 1. We find that for almost all the points we took between 0 and 1, the agreement is rather impressive, or well, I should say good. But we find that it's somewhat worse near when we approach 0. However, this is to be expected because near 0 the T-channel expansion is known to fail. So when we are far enough from the problematic points, we find a good agreement between both channels, and thus we conclude that this function also does satisfy crossing symmetry. And this in turn, well, let me discuss this in the conclusion. So where are we now? Starting from the assumption that we had degenerate OPEs, first we found generic constraint on the non-diagonal sector of the spectrum of a non-diagonal theory, and in particular we found that non-diagonal fields must have a specific form determined by 2 half-integer numbers. Furthermore, imposing the degenerate crossing symmetry constraints, we found the equations that determine the 3-point and the 4-point structure constants, and we were actually able to find an explicit solution for the 3-point function. Furthermore, we related the solution to the known structure constants in the diagonal case. Then, studying a limit of the non-diagonal minimal models, we found an ansatz for the non-diagonal spectrum of a theory, which of course satisfies the constraints we found in the first place. And finally, we computed generic crossing symmetric 4-point functions, providing evidence for the existence of a consistent non-diagonal CFT for a central charge with a real part less than 13. So in conclusion, we actually managed to add not only a new point to this plot, but actually we could paint a whole different region starting from here to the left, in which we think there is a consistent non-diagonal CFT, but there is still some things that we need to know. For example, we did not determine what the spectrum in the diagonal sector is, and we need to determine this part in order to completely paint the picture of this consistent theory. So we need to determine this missing sector of the spectrum and check that it is still crossing symmetric with the pieces we know. And furthermore, we found this spectrum by taking a limit from the minimal models to irrational central charge. But we would like to know, first of all, to formalize this procedure and see if we can also apply it to the diagonal sector of the spectrum. This might give us a hint of what we might find here. But also, it's interesting to try to recover from this point the known minimal model. So this would mean that the theory that we found sort of can be used to interpolate between other known solvable models. So this is what we are attempting to do right now, and thank you very much, and I'll be waiting for your questions. Yes?
So there is a Coulomb gas version of this correlation function. amounts to taking an or before.
Here you mean?
Yes.
Uh-huh.
So is there any way of connecting that point of view?
I hope there is, but we have not explored this feature.
Do you think that you will have non-zero spin solutions for the E series?
We actually have not attempted to do that. I think first, at least I would like to better understand the case of the D theories, in which we already have one piece. But yes, that could be done afterwards. But I
You cannot
yes.
take a limit, right?
Yes.
It's finite, right?
Yes, yes, yes. Yes, you're right. Okay. Yes.
And I have another question. What is special with point 13 in your?
Oh, this is because you see the central charge of the minimal models. First of all, it takes this form. So we are always in this sector here, and by taking this limit, we will never go above. But furthermore, we need the central charge to be less than 13 to keep the parameter beta real. I think I have an extra slide here. Yes.
But this factor you subtract from 13, it's never zero, because it's something plus inverse.
It takes limits, so it can be zero. It's taking limits.
So if I go far enough in taking, yeah. Yes. Okay. Well, then we should modify this a bit. But what we need is to keep the parameter beta that appears here. We need to keep it with a.
It's complex then.
Complex, but not zero.
No, I just want to write zero.
You mean, okay.
Well, but we need the parameter beta to have a positive real part in order to ensure that the 4-point function will converge. Otherwise, we miss this. So this is actually why we want to keep. I mean, aside from the limit, once we are in the limit, we need this to happen in order for the 4-point function to converge, in principle. Otherwise, we cannot ensure that. Yes.
Some you have shown the result with this four-point correlation function, where you check numerically this crossing symmetry.
Yes.
How explicit? Do you have some kind of explicit expression for those four-point functions?
Yes, we did, but I don't have them at hand. In the end, we found that it was more practical. Yeah, it's not here. We found that it was more practical to compute them numerically by iteration. So we didn't work with that, but we could. In particular, for the 4-point functions that involve only two different fields, you have the geometric mean relation. So you can express it as a product of Liouville 3-point functions. But otherwise, you have to build it. It's just playing around with double gamma functions, and you will produce the solution.
We did try to look for the Melian representation, but you probably know there was a lot of people now looking for conformal bootstrap in Melian space.
Mm-hmm.
Try to convert the correlation function to Melian space.
Uh,
But in this case, you will have much simpler expression. Did you try?
No, we have not tried, but it's a good suggestion. Thank you.
Maybe it's the same question as here, this idea of D and A. Is the A series, the diagonal series, well understood in this region?
Not. The problem there is, if you want to try to take a limit of the 4-point function and of the spectrum that appears there, in the A series you have only diagonal fields. So their dimension takes this form. And the problem here is that since you have this sign over here, the total dimension will not go to infinity uniformly as R and S go to infinity. So it's, in this sense, it is harder to study this limit, because you cannot say that, I mean, we think that there is a way around this, but we have not explicitly found how to take this limit, because you need to say that all the terms that would spoil this convergence should somehow die, but it's trickier. We think that since the momenta become dense again on the real line, you could end up with a continuous spectrum. And the hope is that to reproduce Liouville, for instance. But yes, this is only a conjecture. So for the non-diagonal part, it's easier because you have this, and you can say that the four-point function will converge. So that's why I only talked about that, which is the stronger part of the procedure. Thank you very much. Oui.
Après toute cette méthode utilisant des limites,
Oui.
ça soit même difficile de retrouver le cas dont on est parti
Oui,
finalement.
oui.
C'est bizarre,
Bon,
ça.
ça arrive, mais on n'est pas encore fini avec
C'est parce
toute
que
l'analyse.
le modèle de c'est pas de 3 états,
Oui.
c'est D4
Oui.
à 5. C'est la première
Oui.
série D intéressante. On connaît tout là-dedans.
Oui.
On connaît absolument tout.
Oui.
Donc peut-être ça serait l'endroit où commencer.
Oui, bah, par exemple,